Welcome. Today's notes worksheet is entitled Exponential and Logarithmic Regressions and Logistic Functions. We'll have the opportunity today to take a look at some data sets that are exponential and logarithmic in nature, and we'll use the graphing calculator to mathematically model them. So let's go ahead and grab that graphing calculator and then immediately take a look at example 1 and see what variable quantities are related together here. So example 1 states, the table gives the life expectancy of a woman born in each given year. And so here are two variable quantities, just in terms of one depending on the other. I think we could all argue that the life expectancy is dependent on the year born. So life expectancy, let's put as the y, and then year, let's go ahead and put as the x. And so what we're going to do is go through our three-step process, of course. We're going to enter the data, view the data, and model the data accordingly. In this case, for letter A, it states what type of model that we're going to go ahead and use. And we have to be a little careful with the logarithmic regressions here. As it says, we're going to start with 1910, not as year 0, but as year 10 in the model. So typically we start this as year 0, and then from there we go forward. But in this case, as you'll see, we're going to need to do this as year 10 as opposed to year 0. And I'll go into why that is after we get our model. So let's bring up those graphing calculators. Again, please get some practice with this with me, and make sure you're comfortable pulling this off. So first order of business, guys, is go into your y equals. Just make sure anything you have in there is cleared out. Let's turn the stat plot on. So I'm going to just do it right here. Just go ahead and hit enter on that. And so now this should be highlighted. And hopefully it's set up as L1 and L2. And so then let's go ahead and get our data in place. So stat and then edit. And of course, as we said, we're going to start at year 10. So 10, 20, 30, 40, 50, 60, right up the line there. I think this data set ends in the year 2000. And so that'll be year 100 actually on this model. All right, so I'm sure you can type in quite a bit faster than I can. So let's get those x's in there. Here we go. Looking great. Okay, getting closer. And then year 100, I guess. So that would be the year 2000. And then I'm going to have to move my calculator a little bit, but I'm going to go ahead and try to get my life expectancies in place, and please do the same. So into the L2 they go. So get those in, make sure you type everything correctly. I'll try to do the same up here. Sometimes the pen that I use for this is a little picky on how it hits those buttons, but hopefully I can get everything accurate. Okay, getting closer. Again, see, there we go. That's the problem right there. Nice. Got that. Let me make sure I get all the others. Okay, and one more for me. Hopefully you have it in place as well. All right, make sure it matches up there. Mine's looking great. So data is entered in the calculator at this stage. Now what we want to do is go ahead and view it. So as long as your stat plot is on, you go stat. I'm sorry, actually let's go zoom now to view it. And so under zoom there, typically it's number 9, just depends on which model, but just make sure, of course, you have the zoom stat at some point. So there we go. We get something along these lines right here. And, you know, I wouldn't say it's ideally logarithmic, but it has that nice feel to it. Notice there's some great gains right here. And then we got a little more of a plateau in the later years on this model. So it has that logarithmic feel, if you remember those logarithmic models. Kind of initial growth, pretty strong, and then it starts to level off kind of like that. So we are going to go ahead and throw a logarithmic model onto this function. And so now's the third step. And we go into stat. Now I got it. Move it over to calc. And here are all the different types of functions that we've been exploring. And so there we go. So there it is right there. And notice right away you can tell that it's going to do this logarithmic regression in base E. So there's the natural logarithm right there, ln reg. So let's go ahead and get that going. I like pasting it into the y1. I'm sure I've shown you this before, but it's up to you what you want to do. I hit vars, go over to the y, make sure you paste it in a y1, and then it's looking pretty good. And so I'll go ahead and take a look at this out to about 3 decimal places, see if I can get this going. But basically here is the format for the regression that the calculator chooses. Here's your A value, here's your B value, times the natural logarithm of our input. So I see it as 17.594. So let me get that together. 17.594, and then plus, sorry, I'm going to need to bring my calculator up one more time, and it looks like 13.424x. So 13.424 times the natural logarithm of x. There we go. Now one thing to note on this, and then let you do just a quick prediction before moving on to the next piece. Remember what I stated at the beginning. Typically when we do data sets, we always start that initial year as year 0. But in this case, I said, wait a minute, we have to be careful. I want to actually do it as year 10 as opposed to year 0. Now take a look at the regression that the calculator gave us, and can you think of why? Why wouldn't I have wanted to start at year 0 here? Okay, well think about logarithms, everybody. Remember one of the primary conditions with logarithms. Can I ever take the logarithm of 0 or a negative? No. I can only take the logarithm of a positive number. So by putting in 0 as my initial data point, I would have made the calculator do something that that's simply undefined. And so as a result, no luck. So anyway, we kind of just shifted over, and it just works out nicely there. And as a result, you can just use whatever year you were born in and actually use that year. So if you were born in, say, 1995, use 95, and you'll plug it in right here. And so that brings us explicitly to letter B. It does say use the model to find the life expectancy of a woman born in the year that you were born. So in this case, what you're going to do, again, X is going to be the year born. Take that year, whatever it may be, and all you have to do is put that in for X and just do the calculation. So 17.594 plus 13.424 times the natural log of whatever year we're talking about. So if you don't mind, obviously it's tough for me to do that at this stage, but if you can do that, that would be great. All right, very good. So just a nice logarithmic model there. Works out pretty well. Let's do one more, and then we'll get into the exponentials. So example 2. The table shows the relationship between the population of a city in thousands and the walking speed in feet per second. Fascinating. So 2 variable quantities related together here. And so essentially you can kind of see the larger the population, the faster people walk in that city. And you can kind of see the relationship right there. Again, 2 variable quantities related. I would argue that the walking speed of an individual in a particular city is dependent on the population of that city. So same deal. There's your Y, the dependent, and there's your X, the independent. Perfect. Nice short data set here. Why don't we get this in place and then go ahead and utilize it. So I think we're pretty much all set. Again, 3 steps, guys. You can pull it off. Enter, view, model. Let's go for it. So go up to L1, clear, and enter, of course. Go up to L2, clear, and enter, of course. And let's get that data set in. X is first. So population, so this would be 5.5 thousand people, 14,000 people. So data collected on these 5 cities, it looks like. And so a population of 138,000 people, and then last, a population of 342,000 people. All right, very nice. And let's see. So somebody who lives in a city of 5,500 people walks an average of about 3.3 feet per second. Interesting. So again, a little slower pace. And then starts to move up a little bit. People get faster and faster. The more dense the population is, the more people living in the city. And so let's get those together right there. And there we go. Not too bad. Quick data set in place. Entered it in. Guys, it's time to go ahead and view. So zoom and number 9 if you get a chance. And you can kind of see that same logarithmic pattern right there. Okay, initial growth really strong and then starts to level off quite a bit. So I'm liking the idea of a logarithmic model for this. And so let's go ahead and do the exact same thing we did before. So everyone go to Stat, please, if you would. Move it over to Calc, and move on through some of these. Linear, quadratic, cubic, quartic. There it is. So there's our natural logarithm function. And let's go ahead and get that in. I'll put it into the y1. If you don't want to, don't worry. And there it is. Okay, that looks great. So same format, obviously, as example 1. We have our a, b times the natural logarithm of our input. So let's go ahead and get that going. I think I've got it. I'll go to 3 decimal places again. So it looks like the walking speed is equivalent to 2.735 plus 0.352 times the natural logarithm of the population of the city. And so again, what we're trying to do is come up with an overall mathematical model for the individual data points that we have right here. And then obviously once we have that overall mathematical model, we want to utilize it by making some type of prediction, either interpolate or extrapolate. And in this case, we're going to go ahead and do Boulder here, and population I've got is 91,000. So we would call this an interpolation, meaning the population is within our data set. So 91 would kind of fit right in here. And we'll go ahead and see what that would look like. And so let's go for it. Population is definitely just the x value. So nice and straightforward here, everybody. If you didn't pull it off on example 1, I'll give you a little more guidance on this one. So in this case, how about just 0.352? And again, I think we don't want to use 91,000. I think we just want to use 91 because the population wasn't in thousands. So according to this mathematical model, the average walking speed of a person in Boulder, let's go ahead and take a look. So I have 2.735 and then plus 0.352 times the natural logarithm of 91, and there we've got it. And you can see it fits perfectly within our data bounds as we had anticipated, and so we end up getting about 4.32 feet per second. All right, very cool. So we used a fairly small data set to come up with a logarithmic regression, and then we obviously utilized that logarithmic regression to make a prediction. Very, very nice. So we've got 2 logarithmic models under our belt at this stage. Let's go ahead and switch gears and do an exponential model. Probably the most prevalent data set that goes with exponential models would be population. And so in this case, what I did is did a little research and came up with the world population from, let's see, 1750 all the way out to the year 2000. So we've got this piece right here. So a very long time period here. What we're going to do is track population of the world. And we're going to go ahead and see the exponential nature of population growth. And then obviously come up with an exponential model for it. All right, so if you are ready to roll, let's go ahead and get right back into it. Same deal, guys. Let's clear some stuff out and go to that right there. Okay, so let's see. Just go up to L1. I'm going to hit clear and enter. Go up to L2, clear and then enter. And by the way, I've got maybe something in there. I'm going to clear that out as well. Okay, now I'm ready to roll. So population of the world. Let's see what we've got. 1750 is our year 0. On exponential models, we can start at year 0. So I can raise something to the 0 power. I just can't take the logarithm of 0. That's the issue. So this one's not a big deal. So 1750, and then this one would be 1800. This one would be 1850, and then 1900, and then 1950. Doing great, and then kind of going up every 10 years from the census taken. And so I've got 1960, 1970, 80, 90 there, everybody. And last one, I've got a data point in the year 2000. All right, great. And you can see just the dramatic growth over the last couple centuries here. So in this case, it's in billions. So less than a billion in 1970. In 1750, less than a billion. By 1800, still less than a billion. Getting closer though, and then obviously we hit that magic billion mark right there. Okay, got that. And let's match them up. Again, I'm sure you're quicker at this than I am, but I'll see if I can do this in a reasonable time. Okay, getting closer. Okay, I'm going to have to look at my sheet here. Here we go. I've got it. And the last one for me. So in the year 2000, it looks like the population had reached over 6 billion. Unbelievable. All right, so we've got that in. We'd love to view this, actually. So I'm going to hit zoom and number 9. And we've got that piece right here. And again, this is kind of the nature of exponential growth. Pretty flat initially. But the longer we're into our model, the steeper and steeper and steeper the growth is. And so let's go ahead and put a model on this. So when you get an opportunity, go ahead and hit Stat, and let's move it over to Calc, of course. And I think we'll have to go just a little further than where we did before. There's Logarithmic, and there we go, right below it. Exponential regression. It's going to give us an exponential in base B, and so we'll go ahead and actually use that. So here we go. I'm going to do my y1 again. In fact, I don't think I really utilized that before, but maybe I'll do it this time around for us. Okay, that looks absolutely stellar. So there's our exponential model. There's the one we've been investigating, y equals a times b to the x. And let's get that in place. I'm going to go several decimal places out here. It's up to you what you want to do, but essentially the population is equivalent to, I have about 0.6396, kind of our initial value there, using all those models, or using all the points in the data set. And then I've got 1.00807, essentially, raised to the x. Oh, absolutely amazing. And you could see how, you know, this is a fairly low growth rate. Remember this, just year by year by year. I guess if I asked you to translate this, could you tell me by what percentage the population of the world increased from one year to the next over the 2.5 centuries? So remember how this works, everybody. This right here is our growth rate, and our growth rate essentially is 1 plus r. And so I see r as 0.00807, which as a percentage, and here's what's kind of fascinating about this, it's less than 1% per year. So the population of the world has been growing, just according to this model, by less than 1% per year. But again, you can see over such a long period of time how powerful that growth can be. Here, just 250 years ago, we were less than a billion people. Now we're over 6 billion by the time we hit this. And as a matter of fact, at the time of the posting here, we're over 7 billion. So you can see just the way that the growth rates work. And exponential growth, it's pretty crazy. Okay, I'm going to go ahead and do this just per year, and then let's get on to our next piece. So long term, and watch this piece. It says predict the population in the year 2200, and so let's kind of take a look at this. This is obviously going to be an x value, of course, and I should have done this before, my apologies, but I think we all realized population is the dependent, and time would be the independent. But regardless, this is going to be our x value. And if we started in 1750, I keep doing that. If we started in 1750 there, I'm looking at 450 for this. So an x value of 450. So let's go ahead and do exactly that piece. 6396. There's our b value, that magic growth rate. And let's raise it to, what did I say there, the 450th. Something along those lines right there. So I'm going to bring up my calculator and do that once. Oh, and by the way, just while I have it, you can kind of see here, this is the exponential model. Not an ideal fit. It looks like it's a little high on this end. And actually, scarily enough, it's a little low on this end. It looks like the growth is greater than what this model is suggesting right here. But essentially, that would be the fit of our data set to the model. Well, let's go ahead and do this particular calculation that I have, and then there's definitely a follow-up question to it. So I have the 0.6396 and then times 1.00 807 raised, and that's going to be to the 450. All right? And so if you take a look at this stage, population of the world in the year 2200, according to this model, would be about 23.8 billion. Again, think of the issues that we're having now, and population is over 7 billion. So look at the follow-up question, of course, guys. Is that reasonable? Is it reasonable for the population of the Earth to really reach 23.8 billion? I don't see that happening. I feel that that is not a reasonable number based on our history. So it brings up one particular point, that exponential models, as amazing as they are and how well they work for particular quantities, especially population, there is a limitation to it. And so that's what we're going to explore on the back side. So we get into what is called a logistic growth model. And here's obviously exactly what I was talking about. It is a model taking into account that exponential growth is limited. That pattern on the world's population simply cannot continue indefinitely. And so this happens to be shown with what we would call a horizontal asymptote and a logistic growth curve. So there are a variety of population models out there. Logistic model for population just happens to be one of the more prominent ones. And so that's the one we'll go ahead and explore. So we'll take a look at this just in terms of a graph, just get an idea of what it looks like, come up with an equation, and then maybe utilize it a touch. So here's how it plays out. So the idea is that it's growing exponentially initially. And that's the idea right here. Here's the population growth. But at some point in time, again, that pattern simply cannot continue indefinitely. And so what happens is it starts to level off. It starts to change. And so it starts looking like that. And the way a logistic function works is it approaches a particular ceiling, a particular horizontal asymptote right up there. Okay? And so that horizontal asymptote we're going to call y equals c. That's going to be our c value for this. And that would be what we would call the carrying capacity of a particular population. So it's coming up, it's coming up, it's getting closer and closer and closer to this value, infinitely close to that value. But it's saying this is the ceiling for a particular quantity. Okay. There happens to be, well, actually, let me just write one more thing. Sorry, just looking at my sheet here. So the idea is as x approaches infinity, as x gets larger and larger and larger, the y values approach that carrying capacity. They get closer and closer to whatever number that is. Okay, so that's how a logistic growth model would look on the coordinate plane. And obviously what we want to do is come up with an equation to fit this graphical pattern on the coordinate plane. And this is what it looks like. So y in terms of x, of course. And we have our c value on top. So keep that in mind. Here is going to be the limitation right here. And then it's going to look like this. It happens to be written in base e. So coefficient right there times e raised to the negative bx, something like that. So what we're going to do, obviously, is revisit the world's population, and taking into account that exponential growth is limited, cannot continue indefinitely, what would the logistic model look like for the world population? So I just narrowed it down basically to the last half century on our data set there. So we'll go ahead and plug that in. And notice, guys, one more regression coming our way today. Let's go ahead and do it as a logistic. So do this one with me as well, please. Let's go back. And actually, let's go to the y equals, clear that out. And if you would, everybody, stat edit. I'm going to have to clear them. This is a short data set, though, so no big deal. Clear and then enter. And let's go get them, everyone. Type. Fast as the wind here. Got to do it right, I guess. There we go, 20. Got it. Looking great. Good deal. So this is the exact same data set from the previous slide there. Obviously what I'm doing is honing in on just the last half century. And if this pattern continued, what would be the carrying capacity of the population of the world? Again, according to this model and just according to this data, obviously these things are in flux. But let's see. All right, getting a little closer here. You've probably typed it in already and just waiting on me. You have the beauty of fast forwarding if you need to. But all right, I've got them in. A quick peek at that would be great. So there we go. Here's kind of that exponential growth situation, but I want to see it limited. I want to see it plateau. And so let's go ahead and do that piece, everyone. Let's go stat, move it on over, and watch how far down we go here. So we saw logarithmic, we saw exponential, skip power, and there it is in all its glory, logistic. So it's going to actually take a little time to think. This one's such a complicated model. It actually takes a little time. Actually, this one was relatively fast, but it got it all taken care of. There we go. Take a look, guys. There's your C, and there's your 1 plus a times e raised to the negative bx. That's looking perfect. Let's go ahead and get that model going. And let's see. I have, again, just to as many decimal places. I've got the C value now as 14.430. Here's my 1 plus, everybody. 4.727 times e raised to the negative 0.025x. And there it is. Pretty complicated model, isn't it? But actually, it looks really, really nice. We'll look at this on the calculator in just a little more detail momentarily, but let's keep it simple. According to our model, what is the carrying capacity of the world's population? What is the limit there? Well, just according to what I see, and if you look at the way I expressed it up above, there it is, guys. I mean, you know, I don't think the population, you know, can grow indefinitely. And according to this model, the carrying capacity of the world's population is about just over 14 billion. That would be double what we have right now, so that's an interesting projection. All right. Very cool. Let's just take a peek at that graphically, and then we'll just do a little algebra on the last piece. So I've got this. There's the logistic model fitting it short term. Guys, let's see it long term, and just, you know, you don't have to do anything here. What did we go out to? I think it was about 2,200, give or take, somewhere in there. Well, I'm going to go out several hundred years on this, and then obviously have to increase this piece right here. Just take a peek. Let's see if it works. Yeah, not too bad. So you could start to see sort of the nature of the exponential growth, and at some point it shifts and changes, and it plateaus dramatically. And so here, everybody, is your 14.43 right there. And you can see if I hit a little trace on this guy here. Let's see. Let's see if I can get a little closer to this. Nope, never mind. There we go. Actually, not too bad. You can see there, as I go out further and further and further, you can see that population should be getting closer and closer to what we specified, the 14.43. All right, beautiful. Hey, one more piece, and then we'll wrap this on up here. Example 5. So we've got one logistic function, and this describes the number of people, so dependent variable, the number of people who have become ill with the flu T weeks after its initial outbreak in a town with 30,000 inhabitants, hence your carrying capacity. There's your 30,000 right here. And so you can kind of picture what would happen with a flu outbreak. You know, the nature of the growth there would be quite dramatic initially, and then obviously more people are informed about it and are able to take precautionary measures, and so it really starts to plateau from there. The growth decreases dramatically in terms of getting closer and closer to that 30,000. Okay, so just letter A and letter B. Let's go ahead and do it. One, I'll give you the input, you give me the output, and the second one will switch. So letter A, how many people became ill with the flu when the epidemic began? This would be a t-value of 0, by the way. So just that would be the case. And let's just let the calculator do the work here, everyone. You just have to be a little careful with parentheses and stuff like that. But let's go back and pull this off. Actually, I have a few numbers typed in already. So everyone, if you would, let's take the 30,000 and divide. All I need is that t is 0. That's it. T is going to be 0. So just big parentheses around the bottom. That should suffice. So I have my 1 plus 20, and then e raised. There we go, guys. Notice it's set up for it already. So e raised to the negative 1.5 and then times 0. We're going to make t 0. Close that off right here, and then I'll close it off one more time for this one right here. So take a look at how I type that in. Just make sure it clicks for you. And again, all we're doing when the epidemic began is saying that t is 0 and letting that work. And so you can see basically in the initial outbreak here would be about 1428, 1429, right in there. You can round obviously to the nearest person. So when t is 0, we let that just ride there. Nice and straightforward putting that in. Okay, very cool. Letter B. After how many weeks did 1/3 of the population become ill with the flu? You know what, actually, let's just change this now that I'm kind of looking at the numbers here. Guys, let's change this to 2/3 if that's all right with you. There we go. So 2/3 of the population become ill. So that would be 20,000. Actually, no, I stand corrected. Let's go back. Let's just do the 1/3. Yeah, there's no reason not to. Okay, so 1/3 would be 10,000 there. That's fine. I was thinking of something else there, but this should work just as well. So guys, in this case, we have the dependent variable. So let's go 10,000 right there and solve away. Now let's see what your algebra skills are like in this case, because we have some interesting things going on here. So I would ask you this. You know, we haven't really looked at logistic models before, but use a little algebraic intuition. Solve for t. And I see a couple of major dilemmas for t here. Number one is it's stuck as the exponent attached to this base e, so that's not good. And number two is that it's part of the massive denominator here. It's in the bottom of a fraction, so I think we're going to have to remedy both those things. Well, let's do it. Let's remedy first things first. Let's get it out of the denominator. So guys, I'm going to take this entire thing and multiply it on up to the other side. So I have 1 plus 20 times e raised to the negative 1.5t, and that's times 10,000. And that equals 30,000. So I brought the whole thing on up. Now, almost in the same breath, and if I was to do this, I would do it in the same breath, I think we could go ahead and bring this 10,000 back on down by dividing by 10,000. Is everyone okay with that? Divide by 10,000, divide by 10,000. So this comes up, this comes down. And so we get 1 plus 20 times e raised to the negative 1.5 equals, and again, just bring that 10,000 down, and 30,000 divided by 10,000 is just 3. So yeah, I'm actually glad we stayed with the 1/3 there. Not sure what I was thinking in changing it. I like this. It works much better. Okay, so guys, here we go. Let's make it work from here. One problem solved. Now we've got to get t. Let's start unwrapping all this stuff that's right here. Bring over the 1, everybody. So subtract 1, e raised to the negative 1.5t, and I have a 2 right there. That's nice. Divide by 20, so e raised to the negative 1.5t, and guys, 2 divided by 20, I'm seeing as a 0.1. Okay, very nice. I'm going to have to just bring this on up here. Hope you don't mind. Actually, I'm going to rewrite that. E to the negative 1.5t equals 0.1. Looking good. Now it's up to you. What do we do? Let's get that t out of the exponent there. What should I do with this e? Well, I do my old circle and roll. Here we go, guys. It rolls to that other side. Absolutely perfect. And I get the natural log of 0.1. And I hope everyone's okay if I go ahead and just say whatever that natural log of 0.1 is, I'm going to divide that by negative 1.5. And so I'll do that in just one step right up here just to make that work. And then I think we've got it. Let's see. Natural log, 0.1. Let's close it off right there, of course. And then divide by, I think I saw that as negative 1.5. And there we go. So after how many weeks will 1/3 of the population become ill with the flu? Just over 1.5. And there you go. With any model, given the input, you come up with the output. Given the outputs, you come up with the input. Wonderful. Alrighty, so some good calculator work here and an introduction to a new family of functions, the logistic function. Very cool. Please, again, get some practice with the technology, and I'm really good at troubleshooting anything with those graphing calculators, so let me know if something comes up. Thanks so much for listening.